Welcome to the Deep Dive. Today, we're strapping in for a journey into physics that's, well, both really foundational and pretty futuristic. We're talking about the 2025 Nobel Prize in Physics. It went to John Clarke, Michel H. Devoret, and John M. Martinis.
That's right.
And it recognized this critical discovery they made way back in the mid-1980s.
Yeah, groundbreaking stuff. It basically proved that the really deep weirdness of quantum mechanics, the probabilistic nature of reality.
Right, the fuzziness.
Exactly, that it isn't just stepped down at the level of tiny atoms.
No.
It can actually be engineered. You can harness it, observe it in an electric circuit you could, well, literally hold in your hand.
Which is kind of mind-blowing when you think about it.
It really is. A truly watershed moment in experimental physics.
So the core thing, the Nobel Committee highlighted their demonstration of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit.
Right. And let's just pause on that phrase,
Yeah.
macroscopic quantum. I mean, think about that. They were proving that a physical system large enough to actually see, made of billions and billions of particles,
Wow.
could still be governed by a single coherent quantum wave function. That was just a massive conceptual leap and, frankly, an engineering nightmare to prove.
Absolutely. So our mission today is to really unpack that incredible story. How did these scientists take this bizarre probabilistic quantum stuff, the kind of thing Schrödinger was tearing his hair out over, and prove it was actually happening on a scale you could almost touch, a macroscopic scale?
Yeah.
And maybe more importantly, how did that proof become the absolute bedrock for the whole quantum computing field we see exploding today? Driving systems from IBM, Google.
Well, that initial aha moment, that intellectual spark, is just so important because it flew directly in the face of all classical intuition.
Classically, things get big, quantum effects wash out.
Exactly. Classical physics tells you, as you scale up a system, quantum weirdness should just disappear, average out because of heat, noise, interaction with the environment.
Yeah, it becomes predictable.
But what Clarke, Devoret, and Martinis showed was, hang on, if you engineer the environment just right, specifically using superconductors, cooled down to the ragged edge of absolute zero.
Wow.
The entire circuit, the whole macroscopic state, acts like one single quantum thing.
Wow.
They basically found the recipe for making a quantum object visible, defying decades of expectation.
Okay, so let's start where we need to, the historical context. Because the key ingredient that makes all of this possible is superconductivity.
Absolutely essential.
Before we jump into the tunneling part, just give us a quick reminder. Why is superconductivity the physics that let them scale quantum effects up like this?
Right, okay. Superconductivity is the absolute backbone here. You take certain materials, cool them below critical temperature, and bam, electrical resistance just vanishes completely.
Zero resistance.
Zero. And this isn't just some neat material property, it's deep quantum mechanics. The BCS theory Bardeen, Cooper, Schrieffer explains it. Electrons pair up.
Right, Cooper pairs.
Cooper pairs. And the crucial thing is these pairs, they act like bosons, and they all condense into a single unified quantum state.
Like a single wave.
Exactly. You don't have individual electrons bumping around anymore. You've got this massive collective, billions of them, flowing as one coherent, synchronized wave.
Okay.
And that collective coherence is what gives you zero resistance. And critically for this story, it's what gives the system its macroscopic quantum properties. It behaves as one entity.
And that collective behavior leads us straight to the work of Brian Josephson, which happened quite a bit earlier, right?
Right.
Long before our laureates.
Precisely. Way back in '62, Brian Josephson, and he deservedly got the Nobel for this later in '73.
Right.
He theorized what happens if you put a little break in this perfect supercurrent highway. You take two superconductors, separate them with a tiny, tiny insulating layer.
The Josephson junction.
The Josephson junction, exactly. Now ubiquitous. He predicted the microscopic quantum tunneling of Cooper pairs across that barrier.
So pairs jumping the gap.
Pairs jumping the gap. A supercurrent could flow right across the insulator even with zero voltage applied. It was a direct prediction of quantum weirdness. But on the small scale, the microscopic scale.
Okay, so Josephson set the stage with microscopic tunneling. But the really big leap, the one that set up the challenge for the 80s experiments, came from Anthony Leggett in the late 70s.
Ah, Leggett, yes. Another Nobel laureate, actually, for different work on superfluidity in 2003.
Right.
Leggett made this huge conceptual jump. He took Josephson's idea and basically said, what if it's not just individual pairs tunneling? What if the entire macroscopic quantum state of the superconductor The whole collective wave function describing billions of particles could tunnel coherently across that junction barrier.
Oh, okay, that's a big claim.
It was a radical idea. It implied that this collective behavior, this macroscopic thing, could still be governed by quantum wave function dynamics, not just classical physics like heat and noise.
So not just averaging out.
Right. And a lot of physicists were, frankly, deeply skeptical. They thought, look, any system that big is just going to lose its quantum nature instantly. Decoherence would kill it.
So Leggett threw down this theoretical gauntlet.
Yeah.
Prove quantum mechanics still works when the system is big enough to see.
Pretty much, yeah. A huge challenge.
And the team that picked up that gauntlet.
That brings us to the team at UC Berkeley, early 1980s. You had the senior figure, Professor John Clarke.
Okay.
Working with him were Michel Devoret, a sharp postdoc at the time, and John Martinis, who was just starting his PhD.
Grad student, wow.
Yeah, and their mission was crystal clear. Take Leggett's bold theory off the blackboard and make it real in the lab.
Right.
They wanted to basically shift quantum tunneling from this invisible microscopic thing to something you could observe, control macroscopically on a chip.
So it was this mix of like deep theory and really hardcore engineering.
Absolutely. An intergenerational team trying to answer a really fundamental question about where quantum mechanics stops, if it stops at all.
Okay, let's dive into the core experiment itself. This is the heart of the Nobel Prize. They built this tiny electrical circuit on a chip, superconducting materials, centered on that crucial Josephson junction.
Yep.
How does that circuit manage to act like an artificial atom?
Okay, so the key is that this circuit, when you bias it correctly and cool it way down, has specific states. Stable states separated by energy barriers.
Like energy levels.
Kinda, yeah. They focused on the state where supercurrent flows through the junction with 0 voltage across it.
Right.
And they modeled this whole circuit, this collective state of all the Cooper pairs as if it were a single quantum mechanical object. If you map out the energy landscape of this circuit, it looks like the potential energy well of an atom, but a man-made one, an artificial atom.
And they use that famous analogy for this 0 voltage state. Like a ball sitting precariously on top of a hill, trapped by a potential energy barrier.
Exactly, the metastable state.
Classically, that ball just sits there, right? Unless you give it enough energy, enough of a kick to get over the top of the hill.
That's pure classical physics. We call it thermal activation. If things are warm, the ball gets random thermal kicks, right? And eventually, maybe, it gets enough energy to roll over the hill.
And in the circuit, that rolling over means it switches to a state with voltage.
Precisely. But here's the crucial context. Temperature. They were cooling these things down to millikelvin temperatures, almost absolute zero.
Okay, so basically no heat.
Vanishingly small amount of thermal energy. So the classical prediction is clear. The ball should stay trapped forever. There's just not enough heat to kick it over the barrier. It's stuck.
And this is where macroscopic quantum tunneling, MQT, just crashes the party.
Crashes the classical party, yeah. MQT is the quantum mechanical answer to that classical stability. Instead of needing a thermal kick to climb over the energy barrier, quantum mechanics says the collective wave function describing all those billions of Cooper pairs together has a chance, a probability of just tunneling through the barrier.
Like punching through the hill instead of climbing it.
Exactly. It sort of teleports to the other side, even without enough energy to classically make it. And when that tunneling happens, boom, the circuit suddenly flips from 0 voltage to having a measurable voltage.
So seeing that sudden switch happening even when it was freezing cold, that was the goal.
That was the proof they were looking for.
So let's break down that first big experiment.
Yeah.
Actually showing MQT and proving this temperature-independent escape. How did they do it methodically?
Okay, so they took their junction, cooled it way down, then they applied a bias current, slowly ramping it up.
And this current isn't heat, it's more like tilting the landscape.
Exactly. It makes the hill steeper, or rather, it lowers the height of the barrier trapping the 0 voltage state. Makes it easier to escape.
Got it.
Then they just watched and measured the escape current. That specific level of bias current where the circuit suddenly jumps and registers a voltage, that's the point where it escaped the trap.
Okay, and the critical finding, the thing that screamed quantum, not thermal.
They did this measurement over and over across a whole range of temperatures. Crucially, they focused on that transition zone, going from warmer temperatures where thermal effects might still play a role, down to the coldest they could get.
And what happened when they got really cold? Millikelvin range.
Something amazing. Below a certain crossover temperature, the escape rate, how often it tunneled out, stopped depending on temperature, just flattened out, became temperature independent.
Ah,
See, if it was escaping because of random thermal kicks, the rate should have plummeted exponentially as it got colder. Fewer kicks, fewer escapes.
right. It should drop off a cliff.
But it didn't. It hit a plateau. It kept escaping at a constant rate, even near absolute zero. That flat line on their graph at the cold end, that was the definitive smoking gun.
Proof that it wasn't heat making it jump.
Exactly. It was escaping purely via quantum tunneling MQT in a macroscopic engineered system. Just incredible.
It really is staggering. Just thinking about the collective quantum behavior of billions of particles acting in unison like that.
But they didn't stop there. The second experiment pushed it even further. They wanted to show energy quantization.
Right, because if this circuit is truly behaving like one giant quantum system, like an artificial atom, its energy can't be just any old value. It has to be restricted to specific discrete levels, quantized, just like the energy levels of electrons in a real atom.
Okay, so how do you prove that? How do you see these discrete energy levels?
You do spectroscopy. Basically, you shine light on your artificial atom and see what frequencies it absorbs or emits.
But not visible light, right? No. In this case, because the energy gaps are much smaller, you use microwave radiation. You carefully sweep the frequency of the microwaves hitting the circuit.
And you look for spikes in absorption.
Exactly. You look for specific frequencies where the circuit suddenly absorbs energy. Those frequencies correspond precisely to the energy difference between its allowed quantum states, its discrete energy levels.
And did they find them? Did it look like an atom spectrum?
They nailed it. The system showed these clear, discrete absorption peaks. It proved it wasn't just some classical oscillator, which would absorb energy continuously across a range of frequencies.
No, it had specific rungs on the energy ladder.
Perfectly put. It was a multi-level quantum system. A giant artificial atom behaving exactly as quantum theory predicted it should if Leggett was right.
And the sources mentioned there was a bit of a division of labor here.
Yeah, it seems Clarke's group really spearheaded the tunneling escape rate measurements, the MQT proof, while Devoret and Martinis really focused heavily on this high-precision microwave spectroscopy needed to map out these quantized levels. It was complementary evidence, both pointing to the same conclusion: macroscopic quantum behavior.
This whole thing sounds unbelievably delicate. You're looking for these tiny quantum signals.
Oh, incredibly fragile.
And any little vibration, any stray radio wave could just swamp it or fake it.
Absolutely. This is where the sheer engineering brilliance of the prize really comes in. Noise suppression was maybe the hardest part.
What kind of noise we're talking about?
Everything. Thermal noise, obviously, which is why they needed those dilution refrigerators to get down near 15 millikelvin colder than outer space.
Wow.
But also electromagnetic interference, EMI, stray radio waves, signals from equipment nearby, and physical vibrations. Just tiny rattles in the building could disturb the measurement.
So how did they shield against all that? This feels like where the real experimental craft lies.
It absolutely does. They were pioneers in building these ultra-quiet cryogenic environments. For magnetic fields, which can mess with superconductors, they used layers upon layers of mu-metal shielding.
Okay.
For electrical noise coming down the wires into the fridge, they developed incredibly sophisticated filters, sometimes literally using filters made of fine copper powder packed into coaxial lines to just absorb high-frequency noise.
Copper powder. Seriously.
Seriously, and cryogenic attenuators on all the signal lines to damp down any incoming signals to the bare minimum needed. Every wire, every connection had to be meticulously shielded and filtered.
It sounds like building a fortress against the classical world.
That's a great way to put it. They had to create this tiny pocket of extreme quiet and cold, where the quantum effects could actually survive long enough to be measured unambiguously.
Right.
Proving it was real MQT, not just some artifact of noise, required that level of engineering paranoia.
Okay, let's shift gears a bit to the legacy, the so what of all this. Because this work in the 80s is the direct ancestor of the whole quantum computing race today.
No question, it's the foundation.
So the first big impact was answering that fundamental question. How big can quantum systems get before classical physics just takes over completely?
Yeah, it fundamentally redrew the map. It showed that quantum mechanics doesn't just fizzle out at a certain size. If you're clever about the engineering, especially using the coherence you get from superconductors,
Right.
you can make surprisingly large systems behave quantum mechanically. They proved the circuit acted like a single macroscopic particle following quantum rules. It made macroscopic quantum theory a tangible experimental reality.
And their papers, published around 1985, basically kicked off the whole field we now call circuit quantum electrodynamics, or CQED.
Opened the floodgates, really. By showing you could engineer and control these discrete quantum states in a solid-state circuit, they laid down the experimental toolkit for manipulating quantum information on a chip. It was like figuring out the instruction set for this artificial atom they'd created.
So all the techniques used now in quantum computers, controlling states, fighting noise,
It all builds on that foundation. Isolating those quantum levels, controlling them with microwaves, shielding them from the environment, Clarke, Devoret, and Martinis pioneered the essential methods.
which brings us right to the superconducting qubit, the star player in today's quantum processors. Explain that direct line of descent.
It's incredibly direct. Remember those quantized energy levels they measured? The ground state, the first excited state, maybe a second excited state?
Yeah, the rungs on the ladder.
Those are precisely the levels we use today. A superconducting qubit, conceptually, is just taking that artificial atom they discovered and saying, okay, let's use the two lowest energy levels, the ground state and the first excited state, as our quantum bit.
A 0 and 1.
Our quantum Dira wrangle and $1 wrangle. The huge challenge, which the laureates tackled head-on, was making the environment quiet enough and stable enough so you could actually see these levels and then manipulate them reliably without them just collapsing instantly back to classical states.
Okay, let's quickly define the qubit idea again for anyone listening.
Yeah.
Why superconductivity, and what's the big advantage over a classical bit in my laptop?
Right. Superconductivity is key because it provides that essential coherence, making the billions of electrons act as one quantum object.
Got it.
The advantage: superposition. A classical bit is stuck. It's either a 0 or a 1. A qubit, because it's quantum, can be in a superposition. It can be both 0 and 1 at the same time with certain probabilities.
Okay.
And if you have, say, n qubits, they can represent 2 to the power of n states simultaneously. This lets quantum computers explore vast computational landscapes exponentially faster than classical ones, but only for specific types of problems like simulating molecules, discovering drugs, complex optimization.
Right, not for everything. But the magic ingredient that makes this artificial atom actually work as a qubit and not just a simple quantum oscillator is still that Josephson junction.
Absolutely critical. This is maybe the most important technical link between the physics they studied and the technology we have now.
Because if it were just a simple LC circuit, an inductor and capacitor, the energy levels would be evenly spaced, right? Like a perfect ladder.
Exactly. A simple harmonic oscillator has evenly spaced energy levels. If you try to use that as a qubit and hit it with microwaves to go from level 0 to level 1, you'd inevitably also drive transitions from 1 to 2, 2 to 3, and so on, because the energy gap is the same everywhere. It would be chaos. You couldn't isolate just two levels.
So you need to deliberately make the rungs uneven.
Precisely. And the Josephson junction is the key. It's not a linear inductor. Its energy response is nonlinear.
Okay.
And that nonlinearity introduces what we call inharmonicity. It makes the spacing between the energy levels uneven.
Got it.
So you design the circuit parameters just right so that the energy gap between your chosen 0 and $1 angle states is significantly different from the gap between $1 and the next level up, $2 angle.
So you can target the 0 to 1 transition specifically.
Exactly. You can hit it with a microwave pulse at frequency at omega and flip the qubit state without accidentally exciting it up to $2 angle or higher. This anharmonicity is what lets you define and control a distinct two-level qubit within this multi-level system, and it all comes from the physics of that junction they were probing back in the 80s.
Okay, moving into the modern era of actually building quantum chips with these things, let's dig into the core energies that control how these artificial atoms behave. We always hear about E-dollar and E-jallers. What are they, and why is their ratio so important?
Right. E-joule is the charging energy. Think of it as the energy cost to add one extra Cooper pair onto the superconducting island part of the circuit. It's inversely related to the capacitance, bigger capacitor, smaller E-joule.
Okay, cost of adding charge.
Yep. And E-joule is the Josephson energy. That's the energy associated with the Cooper pairs tunneling across the junction itself. It's related to the strength of the supercurrent the junction can support.
And the balance between these two determines the qubit type.
Historically, yes. The ratio EJ-ECC basically defined the different flavors of early superconducting qubits and their trade-offs.
Give us a bit of that history. We know transmons are dominant now, but what came before?
Well, the very first one, demonstrated by Nakamura in '99, was the charge qubit.
Right.
In that design, the charging energy ECC way was much, much larger than the Josephson energy ECC level.
Okay, EC dominated.
Right. This actually gave it really strong enharmonicity, which seemed good for controlling the states. But the huge downside was it made the qubit incredibly sensitive to stray electric charges wandering around on the chip, what we call charge noise.
So it lost its quantum state really quickly.
Catastrophically quickly. Decoherence was terrible. Then people developed phase qubits, flux qubits, operating in different regimes where EGI was maybe comparable to or larger than ECCA. They had better charge noise immunity sometimes, but then they became really sensitive to tiny fluctuations in magnetic fields, flux noise.
So it was like whack-a-mole with noise sources.
Kind of, yeah. The community realized pretty fast that just having good enharmonicity wasn't enough. You needed immunity to noise above all else if you wanted coherence times long enough to actually compute something.
Which brings us to the transmon, the workhorse for IBM, Google, many others. Why did it win the noise fight?
The transmon was a clever design tweak, primarily developed by folks like Rob Skolkoff, Michel Devoret again, Steve Gervin, Andreas Wallraff. They went into the regime where the Josephson energy is much larger than the charging energy. E-Joller, vastly bigger than E-Leller.
Okay, opposite of the charge qubit.
Right. And the key trick was adding a large capacitor in parallel with the Josephson junction, a shunt capacitor.
And making the capacitance bigger makes ECZ smaller.
Exactly. Remember, E-Caesars is inversely proportional to capacitance. By adding this big shunt capacitor, they dramatically increased the total capacitance of the circuit, which in turn dramatically decreased the charging energy EC solars.
And making ECZ tiny makes it insensitive to charge noise.
Precisely. You basically dilute the effect of any stray charges. Now, the trade-off is you lose a little bit of enharmonicity compared to the charge qubit. The energy levels become slightly more evenly spaced.
Okay.
But the gain in immunity to charge noise was enormous. It was a fantastic trade-off. It boosted coherence times significantly from maybe microseconds up towards tens, even hundreds of microseconds in modern versions.
And that made real computation feasible.
That stability boost is really what cemented the transmon and its cousins, like the xmon, as the dominant design for building large-scale processors.
Okay, so we've got our transmon qubit fabricated on a chip, cooled down in the fridge. We need to start a computation. How do we get it into the initial state, usually zero Lie wrangle?
Right, initialization. So the Dirichlet-Wrangle state is just the ground state, the lowest energy level of our artificial atom. And the one-Wrangle state is the first excited state.
Like the levels Clarke, Devoret, and Martinis measured.
Exactly, and initialization turns out to be pretty straightforward thanks to the extreme cold. The energy gap between the wrangle and $1 wrangle corresponds to a frequency, usually somewhere between 3 and 10 gigahertz.
Okay.
At 15 millikelvin, the amount of thermal energy floating around kilobt torr is way, way smaller than the energy of a single microwave photon at that frequency.
So there's not enough heat to accidentally excite it.
Exactly. The qubit just naturally relaxes and settles down into its lowest energy state, the ground state, zero wrangle. You just wait a little bit for it to cool and thermalize, and it initializes itself. Pretty neat.
Okay, now the exciting part. Manipulating the state. Quantum gates. How do you use microwaves to, say, flip a qubit from zero angle to $1?
All right, so control is done with these incredibly precise microwave pulses. They're sent down tiny transmission lines like little wires patterned right on the chip that run near the qubits or their associated resonators.
And the frequency has to be just right.
Spot on. For single qubit gates, you zap the qubit with a microwave pulse tuned exactly to its resonance frequency, that omega energy gap between $0 and $1 angle.
And what does that pulse do?
It drives what are called Rabi oscillations. You can picture the qubit state as a point on the surface of an imaginary sphere, the block sphere. $0 is the north pole, $1 is the south pole.
Okay.
The microwave pulse acts like a magnetic field, applying a torque that rotates the state vector around the sphere.
So you can aim it anywhere on the sphere.
Pretty much.
Right.
If you apply the pulse for just the right amount of time, maybe tens of nanoseconds, you can rotate it exactly 180 degrees, that's a T-pulse, or an X-gate. It flips $0 to $1 or vice versa.
And superpositioned.
Apply a pulse for half that time, a pi2-2 pulse, that rotates the state 90 degrees, putting it perfectly on the equator of the block sphere, which is an equal superposition of $0 and $1. By carefully controlling the duration, amplitude, and phase of these microwave pulses, you can perform any arbitrary rotation on a single qubit with very high fidelity. These are the basic building blocks.
The single qubit gates are essential.
Yeah.
But the real power comes from two qubit gates, right?
Yeah.
That's how you get entanglement. How do you make two superconducting qubits interact on demand.
Right. Entanglement is key. And yeah, making them interact controllably without messing everything up is tricky. Early methods involved just putting them close enough together so their electric fields interacted via capacitance, direct capacitive coupling.
But that's hard to turn on and off
It
precisely.
can be, yeah. And it can lead to unwanted crosstalk. So the state-of-the-art method used in many of the big processors now is something called the cross-resonance gate.
Cross-resonance sounds interesting. How does that work?
It's quite clever, actually, and maybe a bit non-intuitive. You pick one qubit as your control and the other as the target. Then you apply a microwave drive, but you apply it to the control qubit. And crucially, you set the frequency of that drive to match the resonant frequency of the target qubit.
Wait, you drive the control qubit at the target qubit's frequency.
Exactly. This drive makes the control qubit wiggle, and because the qubits have some small fixed coupling between them, this wiggling resonantly pumps energy back and forth between the control and target.
Ah, like pushing someone on a swing at just the right frequency?
Sort of, yeah. It induces a controlled interaction. The state of the target qubit only changes if the control qubit is in the $1 wrangle state. This effectively implements a controlled gate, like a CNOT or a CZ gate, depending on the specifics.
This is better than direct coupling.
It offers really good control. You can turn the interaction on and off just by turning the microwave drive on and off. And it's fast, typically around 100 nanoseconds or so. Plus, they've achieved really high fidelities with it, often better than 99.9% for 2-qubit operations in the best systems today.
Incredible precision at insane speeds.
Yeah.
Okay, last step. You've done your computation, manipulated your qubits. How do you read out the final answer? Measuring a quantum state usually destroys it, right?
That's the classic measurement problem. You can't just hook up a voltmeter to the qubit. The act of measuring would collapse its superposition instantly.
So how do you peak without destroying?
You use an indirect method, usually a dispersive readout. It's quite elegant.
Dispersive readout. Okay, walk us through it.
Each qubit is designed to be coupled, usually capacitively, to its own little microwave resonator nearby on the chip. Think of the resonator like a tiny tuning fork for microwaves.
Okay.
Now, the quantum state of the qubit, whether it's in 0 angle or $1 angle, actually slightly changes the resonant frequency of that coupled resonator. It's a subtle effect called the dispersive shift.
So the qubit's state detunes the resonator slightly.
Exactly. If the qubit is in 0 angle, the resonator frequency might shift down by, say, a megahertz. If the qubit is $1 angle, it might shift up by a megahertz. The key is the resonator itself is a classical thing you can measure.
Ah, so you measure the resonator to figure out the qubit's state indirectly.
Precisely. You send a weak microwave probe pulse towards the resonator. You then measure the signal that gets reflected back or transmitted through. The exact frequency and phase of that reflected signal will depend on the resonator's slightly shifted frequency.
And that tells you if the qubit was 0 or 1.
Yep. By analyzing that reflected signal with standard microwave electronics and amplifiers, you can infer, with very high probability, whether the qubit was in the 0 angle or $1 angle state when the measurement pulse hit.
And it's fast and doesn't totally wreck the qubit state.
It's relatively fast, often takes less than a microsecond, and it's designed to be quantum non-demolition or close to it, meaning it projects the qubit into either 0 angle or $1 angle without adding too much extra noise. The fidelity is typically very high, well over 99% these days. It's the essential bridge between the quantum calculation and the classical result we need.
Looking back at the whole arc, it's just undeniable how much Clarke, Devoret, and Martinis' work accelerated everything in solid-state quantum computing.
Oh, massively.
They proved the fundamental physics worked macroscopically, and then boom, by 1999, Nakamura's team demonstrates the first actual superconducting qubit, the charge qubit, building directly on that MQT and quantization foundation.
It really shifted the paradigm. Before their work, there was just so much skepticism about whether you could ever get a solid-state system to stay quantum long enough to be useful.
Right.
They showed the physics was sound, Nakamura showed the first glimmer of engineering possibility, and it just took off from there. That lineage is why superconducting qubits are, leading the pack now in terms of qubit numbers.
And scalability is always touted as a huge plus for this approach.
Yeah.
Because you make them like computer chips.
Exactly. You leverage all that incredible silicon CMOS fabrication technology developed over decades. You can pattern these circuits lithographically on wafers, create interconnected arrays.
Which means you can, in principle, make a lot of them. How big are we talking today?
The potential is huge. We're already seeing systems from IBM, Google, Rigetti, others, with over 1,000 physical qubits on a single chip.
1,000. Wow.
And IBM, for instance, has these ambitious roadmaps aiming for systems with 100,000 or more qubits within the next few years, targeting 2026, I think.
Goodness.
That potential for high-density integration and manufacturability is a major, major reason why superconducting qubits are still the front runner for building large-scale quantum processors.
But there's always a but. Despite being fast nanosecond gates and scalable, the sources call them delicate powerhouses.
Yeah, that's accurate.
What's the big Achilles heel, the thing holding back the death of computation, and how does it connect back to the noise problems the Nobel laureates were battling?
The big one, the persistent enemy, is decoherence.
Losing the quantumness.
Exactly. It's the process where the fragile quantum state, the superposition, the entanglement just kind of leaks away or gets scrambled by interacting with the environment, reverting back to boring classical behavior.
And this happens because of noise, the same kind of noise.
Pretty much, yeah. Any uncontrolled interaction with the outside world. This causes the state to lose energy that's called T$1 relaxation, or it causes the phases in the superposition to get jumbled up. That's T$2 dephasing.
Okay, break down T$1 and T$2 for us. What's the difference?
So T$1 is the energy relaxation time, often just called the lifetime. It's literally the average time it takes for a qubit in the excited state, $1 angle, to spontaneously decay back down to the ground state, D-wrangle, by giving its energy away to the environment.
What kind of things cause that energy loss?
Lots of things can act as an energy sink. Imperfections in the materials, dielectric loss. A big one in superconductors is the generation of unwanted, unpaired electrons called quasiparticles.
Quasiparticles.
Yeah, even at millikelvin temps, tiny amounts of residual heat or stray radiation can break Cooper pairs, creating these quasiparticles that float around and can absorb the qubit's energy, causing it to decay faster. That's a major focus of materials research.
Okay, so that's T$1, losing energy. What's $2?
T$2 is the phase relaxation time, or dephasing time. This measures how long a qubit in a superposition state, like D$1 plus 1 wrangle square, can maintain the precise phase relationship between the D$ and 1 wrangle parts.
So not necessarily losing energy, but losing the quantum phase information.
Exactly. And T$2 is always shorter than or equal to T$1s because dephasing can happen due to energy loss. T$1 processes contribute, but it can also happen due to interactions that don't involve energy exchange, things like slow fluctuations in background magnetic fields, flux noise, or charges moving around, charge noise. These just mess up the delicate phase.
So T$2s is usually the more limiting factor.
Often, yes. It tells you how long your quantum superposition is actually useful for computation.
And practically speaking, what's the consequence of these coherence times being relatively short? You said maybe 10 to 100 microseconds for good transmons.
The consequence is a hard limit on how many operations you can perform, how deep your quantum algorithm can be. If your gates take, say, 50 nanoseconds and your T22 time is 50 microseconds, that means you can maybe string together, what, 1,000 gates, maybe a few thousand, before the quantum state essentially dissolves into noise.
So you can't run really complex algorithms yet.
Not without help. This limitation is why quantum error correction is so crucial. The idea is to encode the information of one perfect logical qubit across many noisy physical qubits.
Using redundancy to fight errors.
Exactly. Schemes like the surface code might require hundreds or even thousands of physical qubits just to create one robust, fault-tolerant logical qubit that can compute for much longer. That massive overhead is a direct result of these limited coherence times.
So cracking decoherence is the holy grail for making fault-tolerant quantum computers practical. What's the cutting edge of research there? Are people moving beyond the transmon?
Definitely. There's intense research into engineering fundamentally better artificial atoms, often by playing with the circuit geometry and that crucial EJ/EC2 ratio again, but also by using different circuit elements.
Like what? What are the next-gen designs?
We're seeing a lot of excitement around qubits like the fluxonium and the unimon, among others. The fluxonium, for example, uses a small Josephson junction, but it's shunted not by a simple capacitor, but by a long array of larger junctions acting together as a superinductor.
Superinductor?
Yeah, it creates a very large inductance. This design pushes the qubit into a different parameter regime, making it inherently much less sensitive to both charge noise and flux noise simultaneously, which is a huge advantage over the transmon, which mainly tackled charge noise.
And are these new designs actually working? Are they getting longer coherence times?
The early results are extremely promising. Labs are reporting coherence times for fluxoniums and related designs that are significantly pushing past the typical transmon limits. We're seeing numbers creeping up towards, and sometimes exceeding 1 millisecond for both T$N and T22.
A millisecond. That's like 10 to 100 times better.
Yeah. It's a huge leap. If you can get coherence times into the millisecond range consistently, that potentially reduces the overhead needed for error correction dramatically.
Yeah.
It could fundamentally change the roadmap towards fault tolerance. This ongoing battle for coherence, for microscopic quantum perfection inside these macroscopic circuits, is absolutely where the future advantage lies.
Wow. What an incredible journey we've taken. All the way from this fundamental physics question back in the late 70s, can quantum mechanics really scale up?
Yeah, it does apply to big things.
Right. Through the painstaking Nobel-winning experiments by Clarke, Devoret, and Martinis in the mid-'80s, proving MQT and quantization.
Building that visible quantum playground.
All the way up to the complex engineering of today's quantum processors built from those very ideas.
Their legacy is just immense. They didn't just answer a physics question. They showed that quantum mechanics could be an engineering discipline for solid-state devices.
Yeah.
The Nobel Committee said something like, "There is no advanced technology today that doesn't rely on quantum mechanics," which is true for lasers, transistors.
Mm-hmm.
But these laureates showed how you could take the deepest quantum rules and design a system, engineer it, to follow them precisely on a scale you could build and control. They showed us how to write the rules for the quantum dance on a chip.
It really is this beautiful marriage of deep fundamental physics and incredibly precise, almost artistic engineering.
It is. But, listening to our discussion about decoherence, it strikes me we're still fundamentally wrestling with that blurry line between the quantum and the classical world.
How so?
Well, think about it. Why do we see classical physics in our everyday lives if the universe is, at bottom, quantum mechanical? It's because of environmental noise, interaction, decoherence, the very things we're fighting tooth and nail inside that dilution refrigerator.
Ah, right. The noise that kills qubits is the same noise that makes the macroscopic world look classical.
Exactly. So the provocative thought maybe is, what will it really take, both philosophically and technically, to truly conquer that environmental noise, to push coherence times, not just to milliseconds, but maybe seconds, minutes, hours?
Could we ever achieve perfect coherence?
Probably not perfect, but enough to potentially bypass the need for massive error correction overhead.
Yeah.
If we could do that, if we could truly master the quantum to classical transition, what kind of fundamental insights and technological leaps would that unlock? That ongoing battle for perfect coherence isn't just about building better computers, it's about understanding the very nature of reality itself.